Hello, good afternoon, everyone. As she has already described, my name is Gaurav and I work in Tenable. A little bit more about me, I like watching anime and I like exploring different cuisines. So the lunch and breakfast here was really fantastic. I got to try many different things. That was really amazing. Also, the previous talks, which I'll be referencing in my upcoming slides. So let's just continue, right? And a little bit more about me. I do a little bit of I do DevSecOps at Tenable, so it's mostly adversary emulation and then writing signatures, essentially policy as code. So for this specific talk, the agenda is what is Mutant. So Mutant is a programming language. We'll see about it. We'll talk about it. We'll have a live demo and maybe a little bit of live coding. What does it do, and where are we lagging right now? I mean, within the Mutant's context. And what does the future hold? What do we do? What do we want to do after this? Like, what more can we add to it? So, as I said, through Mutant, I wanted to push security completely to the left, right? By pushing left, I mean pushing it left in terms of software development life cycle. So, from the left, well, from your perspective, this is left, right? From the left, we start designing the software, whatever we want to build, and then we build it, and then we deploy it, we test it, and then it goes into production. Traditionally, through runtime security, we check, okay, maybe through bug bounty programs, we find out XYZ application has ABC vulnerability. Maybe it is vulnerable to XSS, or maybe something else. Then if we have to mitigate it, we have to go all the way back, and then we have to fix it. This takes a lot of time, and time is money. So here, I want to push security so far to the left that the developer does not have to worry about it. They only need to write the business logic. How do I do it? Let's see. So I essentially try to add encryption at the compile time and the runtime, but we'll get to those features. Other features include cross-compilation, constant obfuscation, and instead of just talking about it, let's just see how it all works. So we have some sample code, but let's start with something more basic. If you want to write something in Mutant, you can simply use the inbuilt function puts, and you can compile it here. And it generates a bytecode. Now, I like to call it the debug version of our compiled. I like to call it a debug version of our source code, because essentially you still need the Mutant to be installed here. It's going to run in Mutant virtual machine. And it runs. You can simply copy it over to the virtual machine. It will work there. Okay, so while the virtual machine starts, I want to talk about constant obfuscation here. When I say constant obfuscation, I am talking about these. Whatever data you add in your variables. This is your constant. Is it visible, or should I increase the font? Okay. In the back, is it visible? Okay, great, thank you. Now, I think it will be a better idea if we just move forward with a better example. In this case, let's just call it right? And now I'm going to demo cross compilation. So if I want to build for Windows, because right now I'm on Windows, I don't need to specify any other options. We just need to give it a release command and our source code file, which is vault.mut. It will take a couple of seconds to generate our compiled file, and it's here. Let's see if it really works. And it indeed works. But is it really of course, it is a PE32 executable, but we can always verify. So here WSL can help me. It successfully generated a PE32 executable because we are on Windows, but we can always generate an ELF file. All we have to do is specify which operating system we need to use. And it's done. We have generated an ELF binary. Now, when I talk about cross compilation here, as I mentioned, either we can generate a byte code or we can generate a release binary. We just saw all these, right? You can compile this vault file. And this is the bytecode that you get here. You get our header, MUT, and the footer, ANT. These help us in identifying that this is indeed a mutant compiled bytecode object file. We can generate a release binary as well, just like we noticed, but we can also generate a bytecode object file. Try to think of it as something that you would do with Java, right? Java runs in JVM and Mutant runs in MVM. Java virtual machine, Mutant virtual machine. Also, why do I call it Mutant? Because I'm mutating the bytecode in runtime. This part you see right here, this is all of your bytecode. This is the compiled bytecode. While this section is just the hash. It's to verify integrity. But maybe we want to see whether it really works or not. Do integrity checks really work here? So I'll try to modify this bytecode object file a little bit. And let's see. So it cannot identify the file because we have tampered with the file. And if I restore the changes that I made, it works just fine. Of course, we can also generate the executable binary. We have already seen that it can generate a binary for Windows, but it can also generate a binary for Linux, but it can also work on your Android devices. What do the Android devices use? They run on Linux, and a lot of devices might use ARM architecture, maybe ARM64, maybe ARM32. Some of them may use AMD64, but let's try compiling it for ARM64. And as you can see, we have indeed generated an ARM executable here. So this is the cross-compilation part, how you can cross-compile from Windows to Linux. Of course, it will work vice versa as well. If you use Mutant on Linux, you can compile it for Windows or Mac or Android. Or Essentially, you can compile it from any machine to any target machine. Constant obfuscation. Now, this is something where we need to debug a little bit to see what's going on. And here I'll try to explain what I meant by a debug or debug mode in Mutant. Now, you can either have a release binary, which is a self-contained with the runtime and everything of a self-packaged binary. You can send it anywhere. You can use it anywhere. It's just a binary. It's just an executable file. Or you can have a debug file that's that object file. Now that object file is dependent upon Mutant. It needs the Mutant virtual machine. So you need you need Mutant to be installed there for that one. Release binaries don't need it because they are self-contained and they contain the Mutant virtual machine inside of them. It's just like how .NET code generates their self-contained single binaries. They package the .NET runtime within the binaries they are generating, or Go does something similar. It packages the runtime within the binaries. Is this part visible where my mouse pointer is? Because this might be a little bit too small, and I cannot really change the size here. So let's try to debug it. Let me see if we have it. Okay, we have it here. So this demo actually explains two things. First will be constant obfuscation, and second will be the runtime and encryption we have. This is compile time encryption. This is encrypted byte code, right? But when we read it, first the entire compiled byte code gets decrypted, and then individual instructions have to be decrypted only when they have to be used. And we'll see how that works. So, right, as I said, I already mentioned this compile time encryption. We have compiled our object code, and this is right here. This is a compiled encrypted byte code. As for runtime instructions, runtime encryption, individual instructions, or rather individual byte code. So a little bit of theory here. What I'm trying to do is think of them as three states that you have. First is pre-execution state. Second is during execution or execution state, and the third is post-execution state. So first you have the pre-execution state. Here, the instruction is encrypted. Then you go to the next state. It's the execution state. Right now, bytecode has to run, or the instruction has to run. So when it has to run, it needs to be decrypted. So it gets decrypted. When it's done doing its part, when we have received the data, or whatever we had to do, when it's done executing, we go to the post-execution state. During the post-execution state, it gets encrypted again. And we'll see all this. We'll debug our program because we want to see how exactly that virtual machine is working. We want to see the internals. Obviously, this is an open source project, so everyone will be able to see it. Also, just a side note, so I was speaking to one of the speakers before, and they explained it to me that this is how Denuvo works, if you have heard of them. So Denuvo adds anti-tamper, anti-piracy technology to games. It's very all closed source, very proprietary. So this is Denuvo works in a similar way. They are constantly encrypting and decrypting instructions that go to the CPU. So it becomes harder for someone to reverse engineer the games. Here, it becomes harder to reverse engineer any applications written in Mutant. We get the instruction, we decrypt it, we get the opcode out of it, and then we encrypt it again. This is to ensure that if you need the opcode, that is only that should only be done during the decrypted state. So this should only affect maybe a couple of clock cycles. Every time I push an object onto the stack, it has to be encrypted. Now the stack will contain our compiled functions, our constants. Well, I call these variables constants because because as long as during the current execution phase, that specific variable's data does not change. It only changes in a different execution context. So think of these constants as constants to be scoped by time or the execution context. And let's see what constants do we have, or I think we are still adding them to the stack. So at this point, we have this built-in function here. While all the constants are encrypted objects, I hope this, yeah, it looks visible enough. All of these constants are encrypted. We are in memory. This is running right now. We are not in the disk. This is all in the memory. We'll see a better example other than this debugging. Let's compile it again for Linux AMD 64, and let me just remove that file because I'm going to copy to the virtual machine where I'm going to run it. And we have a compiled file. Also, just for fun, let's see if it has the hard-coded credentials or not. We have a situation where we want to get in somewhere, right? And the secret is 42 because the answer to life is apparently 42. So we could not find it because, well, it's encrypted. So therefore, we could not find it within the strings in that binary. Right now, it's on disk. So this verifies that, yes, compile time encryption works, but we want to see this in memory. So let's go over into a virtual machine, and we'll copy it there. We'll capture memory dump, and out of that captured memory, we'll see whether we are able to find the secret is 42 or not. Also, I got this idea of capturing memory from one of the speakers here. So what I'm trying to say is this is an amazing conference, and some of the ideas that I got, like how better I can do, how else I can test Mutant, came from talking to people. So it will be a great. It will be great. So it's one of the perks of networking here. You get many amazing ideas, and let's see how it holds up. So we can copy it from here and we'll need 2 terminal windows. Let's make sure it's executable and then let's run it. So this program is running right now, and I'm going to capture memory. I'm using AVML. It's Microsoft's project. So you don't have to compile a kernel module to capture memory. It's really easy. It's written in Rust. It's amazing. Do check it out if you're interested in memory forensics. And it's going to take a couple of seconds to capture all the RAM that we have here. And it's done. Since I was using root, I have to change the ownership so I can access this file. And let's grab all the strings. It's going to take a couple of seconds. It's like 2 GB of memory that's going through. It's going to grab all the strings and then and it's going to keep it within this string file, and it's done now. So we are going to grab through it. Let's verify that this is indeed the string we should be looking for. And it is, secret is 42. Let's see if we can find it. And apparently we cannot. It is not here. We could not find it in the memory dump. So this ensures that when the program is running, the memory within the memory, those instructions, constants, all the data is still encrypted. That's the reason we cannot read it. But this doesn't explain anything yet, right? Maybe I don't know how to capture the memory, or maybe this is simply not the correct way for analysis, which is why we need to benchmark our results. We need something to compare it with. So I'm going to compare it with a C++ program. But first, let's verify whether this executable file really is working or not. Maybe it's a malformed executable file. Maybe Mutant does not create a correct executable file. So I just need to copy this from here. Okay, it looks like it is creating a correct executable file. It is working just fine. So before we compile our C++ program, let's see how it looks like. Very simple, very standard program. Also, we need to remove this. This needs to be changed so it matches with the same secret is 42. Now I understand that all of you who are watching this talk right now must be cringing upon the fact that why am I hard coding credentials? Sometimes some developers may not be aware of this. Sometimes they just think, okay, no one is going to enter my trusted zone. No one is going to read the server code because it's behind a bunch of firewalls and everything. But what if lapsus happens? What if lapsus happens? What if lockbit happens? What if the data gets leaked? Or what if last pass happens? You remember that a lot of their source code was stolen. Or in this scenario, at least your binaries will be protected against reverse engineering attempts. To some extent, it's not a perfect solution. Someone will obviously figure out a way to break this. Okay, so now that we have modified our C++ code, let's compile it. Okay, and I'm going to run strings here just to show you whether we can find anything out of the compiled C++ file. And yes, we can find it here. It is so this hard-coded string is there in C++ file, even in the executable file. As I showed you before, if you try to find this string within the mutant executable file, which we can do right here, we won't be able to find it because it's all encrypted in compile time and runtime, as we saw before. So let's run this program and capture memory again. And it's going to take up, okay, that was fast. Now I just need to change the ownership. And let's find all the strings. It is a 2 GB memory file, so it takes some time for it to get all the strings out of it. Okay, now we have the strings, so let's see if we can find it. And yes, this is where I believe Mutant works better, because within runtime we were not able to find secret S42 string, which was our hard-coded credential. Obviously, if I capture the memory again and I run the Mutant compiled binary, we'll still find the string, because when we're running the program, it's not just a memory occupied by Mutant. There are other programs like this Vault CPP one. So I'll have to reset the virtual machine for this, but I hope you get the gist of it, like how the runtime and the compile time encryption is being enforced here. But this is still not perfect. This is a POC, it works, things are working here. It's still not perfect, there are some limitations, and let's see what those are. Now, the key generation algorithm is deterministic. Also, it is open source, so anyone can just read how it's working. But even if Mutant was closed source, someone dedicated enough could figure out how the key is being generated. And when they figure out how this key generation is working, they will essentially bypass all the security. Because in Mutant, security here is it bangs totally on obfuscation and encryption. That's all there is to it. However, things can be improved. We can add bytecode compression. We can have so right now all the constants and all the stack is currently static in a way, but we can do better there. We can make them more dynamic, but that's something we can discuss later. Its community adoption is not that great because it's not really a direct plugin for LLVM, JVM, CLR just yet. Many things needs to be improved here, and then maybe we can figure out how to ingest other binaries and other programming languages, so that you don't have to use Mutant programming language. You don't have to change your tech stack just to get this level of security. Also, obviously, this is not battle tested. I have only tested it on my own machine, maybe with a couple of friends, but it's not 100% tested. It's not tested on some really complex critical software, or it doesn't, because I don't really have many people using it. So a lot of testing needs to be done. Maybe there's some side channel attack. Someone can grab the value from CPU cache, or someone can figure some other ways out to get the data from the memory. Those protections still need to be added. What's next? We add Unicode support. We add bytecode compression, and we add a REPL to the website. We have a website here. It's just that you cannot directly run Mutant code there, but in future you will be able to. Also, it's open source, as I mentioned before. You can just head over to this link. You can try it out anytime, clone it, fork it, use however you would like to. And let's connect. This is my username for GitHub and LinkedIn. And if you have any questions, I'll be happy to take them. Yes.
Hello. Hi, very nice talk about virtualization for code protection, right? So why would I use a different language while I can use VM Protect or Thermita-like softwares which can directly convert my code into virtualization code?
Right. So what I'm trying to, as of this moment, I wouldn't want anyone to use Mutant. It's an academic project. It's like an infancy. But in future, I would like a Mutant adoption when it's more feature packed. So the reason I'm trying to provide here is that, let's say you're writing an application Java or something. You should not be relying on many different technologies, many different tools to figure out how to harden it. Sometimes people write assembly code by hand. Sometimes they use different types of packers. Packers can be detected by can be picked up by anti-malware engines. I want to bake the security inside of the language.
Yeah, but like if you heard about VM Protect and Themida like softwares, which are protectors and which use virtualization code as a protection for code security, which is the similar concept you are saying here. So what it does is it will actually compile the x86 byte code or R64 byte code and compile into their virtualization code, and they are like very mature engines. So why won't I make my code same and then use the VM Protect or Themida, which are like battle tested and everything else?
Right, that's a great question, and I need to check those technologies because unfortunately I have not heard of them before.
Second question is, you were talking about that you can convert the code from the applications Java, CLR, .NET, or LLVM plugins so that you can convert the code. So any plannings how you will do that? Because the current research in the devirtualization and virtualization code is like the devirtualization part is very hard because of the code path and the CFG patterns, right? So anything which you have thought about that how you will convert the x86 code into your own virtual machine bytecode or vice versa?
So for now, I'm only planning, in the beginning, I'm only planning to target, say, LLVM or JVM, and then make a sort of plugin for them. I don't want, in the beginning, I don't want to take the already compiled binary and then try to add security to it. That will be really complicated.
Yeah.
So, yeah.
Yeah, okay, got the answer. Thank you.
Thank you.
Anyone else? Yeah, thanks Gaurav for this amazing talk.
Thank you.
What will be the runtime like overhead if we are encrypting and decrypting our code?
Sorry, I could not hear you.
What will be the runtime overhead, like time overhead that we are spending during decryption and encryption?
Right, that's a great question. I was actually expecting it. So overhead right here should be minimal. It's just XOR. I XOR the individual instructions. It happens in like 1 or 2 clock cycles max. There's not much overhead there.
Okay, so you're not really like encrypting with some keys or all that.
XOR by definition should be the perfect encryption as long as we can find the perfectly randomized key. Now, while I do not claim that I have a perfectly randomized key, I believe the size of instructions are small enough to generate a good enough randomized key. So I don't have to use a very complex encryption algorithm here.
Okay, yeah. But so if you are using only XOR, like for a hacker, like or anyone who wants to decrypt it, it will be quite easy, right? You just have to perform same operation XOR, and you will get the original opcode.
Yeah, it's just like you can just run AES again if you have the key. So here you can just run XOR again if you have the key. So it's just like any other encryption algorithm. You have the key, you run it, and you can just decrypt whatever encrypted content was.
Okay, so where are you storing this key then?
I generate this key on the fly. This will be a longer conversation if I explain the key generation process here. I try not to store it anywhere.
Okay, sure. Yeah. Got it. Thanks.
Again, thanks for the talk, and I really enjoyed your description of how you're obfuscating the binary. So I guess one question I had was that how bloated are these binaries that you're generating? And a follow-on for that would be, could you like just show the binary actually, especially the one for Linux? Is it identical to the one on Windows? I would think not, right?
Okay, so let's see what's the size difference between these binaries.
No, I'm just asking you for the size difference. I don't want you to show it, but then I wanted to see what the binary on Linux look like. Like, could you do a hex dump and show it to us?
Sure.
Yeah, thanks.
this is a pretty much bloated binary. So it's like 30 MB in size. This is one of the problems that I need to address. So it is in scope, and in future the binary size won't be so big. The binary size ranges from 30 to 30.1 or 2 MB between all the platforms.
Is it an ELF binary? Is it an ELF binary or?
Yes, it is an ELF binary.
Okay. Okay, cool.
Anyone else?
Can we use other Golang libraries here since you're compiling using Golang, right? So like HTTP, can we use HTTP?
Right now, the features include the features include user-defined functions, some complex data types like arrays. You can have hash maps, and some user interaction, user console input output. As of this moment, I haven't figured out a way to securely perform disk I/O operations or HTTP requests or networking operations. This is a more future feature. But if you're interested in contributing, I'll be happy to talk about it.
Sure, thanks.
Anyone else? I think we're good.
Great. So thank you, and special thanks to my professor. This was my academic project during my master's thesis. Other than that, thank you to the Nullcon team for organizing it. This is a great event, and thanks to you for listening and for all these questions. This really gives me perspective around what more I can do here. So thank you.
Thanks to you, Gaurav, for the wonderful talk.